Oh, there you are. Come on, grab a seat. I got your coffee. And so last time we talked about Java. We started out with variables, we went to primitives, objects, took a look at the stack, the heap, made some decisions with if-else statements, talked a little bit about loops, and gave you a tiny glimpse into virtual threads. So I told you that if uh, if you'd meet me again, that we'd do something a little bit more serious. And so here's where I'd like to introduce you into data structures and algorithms. Now, don't panic. I'm not going to be throwing a giant textbook at you. We're going to sit down the same way that I would teach a friend, okay? We're just going to build something. Remember that cafe app thing that we were talking about previously? Well, yeah. Well, we got a problem. Go figure. So we've got inventory, um, and now we need a way to manage it. So we're tracking some different coffee beans. Okay, we've got espresso, Colombian, we've got decaf, French roast. We've got a little bit of Ethiopian, and tomorrow maybe we're gonna start having some tea, and maybe we're gonna have some few different flavors. Who knows? We'll eventually have thousands of coffee. Whoa, oh, yeah, okay. No, we're getting carried away. So the application just needs to answer a few things. Do we have this coffee? How many bags do we have? And what's the most recently added product? What's the cheapest product? What about products that are running low? Anything? And here's where programming becomes interesting. Because there are a lot of different ways that we could store information. And the way that we're going to choose to store it, we can completely change how quickly the program can work. This is what data structures are all about. So a data structure is simply a way to organize and sort data that we can work through efficiently. So think about our cafe for a second. If I dump every bag of coffee on the floor right now that we own, technically I still have all the coffee. But now finding the specific bag that I want, that's going to be a nightmare. All right, so instead, maybe I organize them into shelves. And maybe I label those shelves and I organize them alphabetically. And then I create some sort of a coffee system where I can jump to the exact coffee that I'm looking for. Same information, just differently organized. And that is the core idea behind data structures. So we're not just asking, how do I store this? We're asking, how do I store this in an efficient way that I can use it later? Now, what exactly does efficiency mean? Um, this is where algorithmic analytics becomes into the conversation, or comes into the conversation, sorry. Uh, this is, you might imagine that we have 10 products. And I search through those 10 products, no big deal. Takes me no time. Now imagine we have 10, imagine we have 1,000 products, maybe 10,000, maybe 10 million. Suddenly, search seems to matter. And this is where you'll hear programmers talk about the big O notations. And you might see things like O1, O log of n, O of n, O of n log n, O of n squared. And when you're first learning things, that looks mathematical nonsense. It doesn't make any sense. It's just numbers and letters. But it's actually telling you and asking a pretty simple question. As the amount of data grows, how does the amount of work our algorithm needs to grow? That's it. O of 1? Let's start out with the easy one. O of 1, continuous time. So imagine I have a shelf with numbered positions, and I tell you to grab me the espresso beans. They're over on the position 7. Well, you don't care that the shelf has 10, maybe 100 different things in it. You just care about position 7. One operation, that's it. One simple thing. That is O of 1. Now, the amount of work does not grow with the size of the input. This is the reason that arrays are so fast. Now, what is an array? Well, an array gives us a block of memory where elements are stored sequentially. So something like espresso, Colombian, Ethiopian, decaf. Because those elements are laid out in memory, Java can calculate where a particular index belongs. So a products array 3, uh, we can jump directly to the location that we want, and that is O of 1 accessed by index. Pretty nice, but there's a catch. What happens when our cafe suddenly gets another product? Our array has a fixed size, and we need more room. We need a larger array, and that's where dynamic arrays come in. So Java has this thing called ArrayList, and this gives us an array-backed structure that can grow. And when it runs out of capacity, it allocates a larger backing array, copies the existing elements, and then it just continues. So most of the time, adding an element to the end of is extremely efficient, but occasionally that resize operation can get expensive. And that is a really important lesson in DSA. As far as the fastest looking operation isn't always the whole story. You need to understand what happens underneath. For example, a linked list. So let's imagine that we don't want one big continuous block of memory. Instead, each inventory item could contain a reference to the next thing. So let's say espresso points to the Colombian, points to the Ethiopian, points to the decaf. A doubly linked set is basically the same thing, a step further, in that each element knows the previous one. So this can make certain insertions and removals very efficient when you already know the source node. But here's the trade-off. If I ask you to get me item 900 and a linked list can't jump instantly there. Instead, it has to walk through the nodes, which is an O of n. And suddenly, we have our first real lesson in algorithmic trade-offs. Different structures are good at different things. Now, let's forget inventory for a second. Imagine the cafe has a stack of orders, and the last order placed is the first one that we want to deal with. That's a stack. Last in, first out. So think of a stack of plates. You put one on top, you take from the top. You don't pull from the bottom unless you really want a mess. Um, Now, imagine customers waiting for their coffee. First in, first served. That is a queue. First in, first out. And Java gives us abstractions for working with these concepts. For queues and double-ended operations, you'll often encounter the DEC, or double-ended queue, and you can add and remove from either end. Again, it's not about memorizing the API, it's about recognizing the problem. Do I need last in, first out? That's a stack. Do I need first in, first out? That's a queue. Do I need them both? That's DEC. Now, let's say your inventory grows to over 100,000 products, and somebody walks into the cafe and is like, yo, do you happen to have Ethiopian coffee? I don't want to start at the first product and then go to the second, the third, the fourth, and keep going until I find it. I want to be able to find it quickly. Now, this is where hashing becomes incredibly useful, and we can create a hash function. And the idea here is that we take some piece of information, maybe the product name, and then we turn it into a value that helps determine where the product should live. Now we can jump closer to where that product belongs, and this is the basic idea of a hash map. Now, um, this is good for the average case. Hash maps lookup are approximately 0 to 1, and that's pretty good, but there's no such thing as free performance. Two different keys can produce the same bucket. This is called a collision. And now our data structure needs a strategy for dealing with that. One approach is the separate chaining, others are open addressing, and as the table fills up, the load factor becomes important. Eventually, the table may need to resize and rehash its entries. And this is why understanding what happens underneath your collections matters. You don't have to have every implementation memorized and implement this every Tuesday morning. But you should understand the basic mechanics. And there is one more Java specific piece that you absolutely need to understand if you're creating objects to use as keys. You need to understand the contract between hash code and equals. If two objects are considered equal, they must produce the same hash code. Otherwise, your beautifully designed lookup system can behave in ways that will make you question every decision that you've ever made. Now, trees. Let's say you have your inventory and it's not exactly as flat as it used to be. Maybe we now have things organized in a hierarchy. So what was flat is now more like we have coffee, we have um, Robusta and Arabic, and underneath Arabic we may have Ethiopian and Colombian, and now it's looking more like a tree. And a binary tree is a tree where each node has at most two children. Now, binary search tree, or BST, gives us an ordering rule. So smaller values go in one direction, larger values go in the other. Now, that can make searching a lot faster and scanning a list. In a nicely balanced tree, you would wind up with something like O of log n. Um, and that's where things can get really interesting. So, because what happens if our tree becomes horribly unbalanced? So instead of 50 at the point, we got 25, 75. We maybe we might end up with something like 10, 20, 30, 40. Yada 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 yada. Well, congratulations. Your tree has basically become a linked list. So we have these self-balanced trees, ALV trees, red-black trees, and they use different balancing strategies to keep these trees from becoming widely inefficient. And once you have trees, you also need to know how to walk through them. That's where tree traversal comes in order, pre-order, post-order, and breadth first traversal. So each gives you a different way of visiting the nodes because breadth first searching naturally works as a queue. And that is one of the coolest things about DSA. These concepts aren't isolated, they build on each other. Now, let's make a problem bigger. So, the cafe doesn't exist in isolation. We have suppliers, we have employees, we have customers, delivery routes, locations, and maybe one supplier provides multiple products, and one of those products happen to come from multiple suppliers. Now, there's no longer no simple hierarchy. We're now into a graph. And a graph lets us represent relationships between things. Um, for example, you have vertices and edges connecting them. And we might represent those relationships with an adjacency metrics or some sort of adjacency list. Um, then we can start asking real interesting questions like, can I get from here to there? What's the shortest route? What depends on what? And now we have some algorithms like depth first search, breadth first search, and Dykenstar's shortest path algorithm. I apologize if I pronounced that wrong. Um, and even topological sorting. So where we can order things based on their dependencies. For example, if we need to prepare something before another task can happen, a graph can help us model that relationship. Kayne's algorithm is one way of performing a topological sort. And now suddenly, we're not just sorting data anymore, we're solving problems. Now, but there's still one other problem. What if our inventory is a mess? We've got coffee, tea, sugar, milk, espresso, cookies, everything. And what if I wanted that to be sorted alphabetically? We need some sort of a sorting algorithm. And there are a lot of them out there. But I want you to understand a few important ones. Binary search can find an item in a sorted data with an O of log n. Merge sort gives us O of n log n behavior. A quick sort also gives us O of n log n, average case. And a heap sort uses a heap to achieve an O of n log n worst case performance. Now, there's a priority queue. Let's say I don't necessarily care what arrives first. I just care that it has the highest priority. Maybe we have coffee orders, regular coffees. Then an urgent catering order comes in, and another regular order coffee. The priority queue allows us to put the highest priority items in front of the other ones. Again, different problem, different structure, different solution. Big picture here. Well, I want you, and I know this sounds like a lot, and it is, but here's what I don't want you to do. Don't walk away from here trying to memorize hash maps are O of 1, binary search is O of log n, and merge set is O of n log n. That's not the point. I want you to start thinking differently. When somebody gives you a programmatic problem, don't immediately jump, what code do I write? Ask yourself instead, what information am I working with? How should I organize it? What operations do I need to perform? And how much data might I have? And of course, how expensive will these operations become if that data grows? So, that is the mindset behind data structures and algorithms. You're learning to choose the right tool for the problem. So, we came into this meeting with a problem. We have a cafe, we have some inventory, and we need a way to manage it. We started with some arrays and dynamic arrays, then we went into some linked lists, stacks, queues, hash tables, trees, graphs, searching, sorting, and of course we talked a little bit about Big O. Now, that's a lot, but not because someone decided that programmers need more math, but because eventually your program does get bigger. 10 items can become 10,000, and 10,000 can easily become 10 million. And a solution that felt perfect on your laptop may all of a sudden start to break when you start getting very big numbers. And that's why data structures and algorithms matter, because making a mistake can become very expensive. And honestly, this is where I want you to spend some time. Okay? I'd like you to play with these structures, implement some of them yourself, break them, measure them, and see how they play. Poke the bear. Once once you understand how and what is happening underneath the collections that you're already using, Java's API becomes a lot more understandable. And we've got ourselves another problem. We've got our language, we've got our data structures, we've got our algorithms. But now, how do we turn this all into a real application, you might ask? Because a cafe doesn't just sit still, it needs to function. We need users, we need persistence, we need databases, we need APIs, and eventually we're going to need to introduce something called Spring Boot. But for now, that's a copy for the future. So, you've got your homework. Go build something. Test the structures. Play with it. Make mistakes. And grow. Keep your curiosity open. Your skills sharp. That coffee cup full. And I'll catch you at the next meetup.